Hello and welcome to this video on identifying how rank, the rank of a matrix relates to the column space and row space of that matrix. So in this video I will redefine rank of a matrix. I've done it in past videos. I'm assuming you've been watching. I'm hoping you've been watching, following along. So I'm going to redefine what the rank of a matrix is, talk about its relationship to the column space of that matrix and the row space of that matrix. And then I'll just go over a couple examples where I'm given a matrix, and then I'll find the column space, row space, bases for the column space and row space, and then show you how the rank is going to have the same, the rank is a number that is the same number of vectors that are in any basis for the column space and row space of a matrix. Okay. So on the first page, just again defining the rank of a matrix. The rank, I'm really defining it in a couple ways here. The rank of an m by n matrix A, the rank of any matrix A, denoted, rank of A, is the number of linearly independent column vectors in an echelon form, so whether it be row echelon form or reduced row echelon form, the number of linearly independent column vectors in an echelon form of A. And these linearly independent column vectors in an echelon form we've been calling the pivot columns in a lot of videos prior. You could also say linearly independent row vectors as well. So I should really add that column or row, because they'll be the same number. The number of, because the pivot positions aren't changing, so the number of pivots you have in a matrix, when you write it in echelon form or reduced echelon form, will correspond to the number of pivot columns and also the number of pivot rows that you have. Alright, another way to define the rank, and what we're going to see in these examples I have in this video. The rank of a matrix A is equal to the dimension of the column space of A, right? And since there are the same number of linearly independent columns as there are independent rows, we'll see that not only is the rank equal to the dimension of the column space, but as well as the dimension of the row space of A. All right. So the rank of A is equal to the dimension of the column space of A, right? Column space of A, which is also equal to the dimension of the row space of A, row space of A. All right. So just got that out of the way. Now I have just two examples here, because I've done a video on rank before. Right? You should know how to find the rank real quickly. You just put the matrix you're given into either row echelon form or reduced row echelon form and simply count the pivots. How many pivot columns or pivot rows does the matrix have, and that's the rank. It's really simple. But this is a video on showing you how the rank is also the dimension of the column space or the dimension of the row space. Okay, so here's matrix A, and I'm asked to find the column space, the row space, and then find a basis for each, right? A basis for the column space, a basis for the row space. Then state the rank of A. Alright, so here A is a 3x4 matrix. And as I mentioned a second ago, right? Now the column space, I could write the column space and row space of A right now, but I'm going to write it with a minimally spanning set in a second. But yeah, so like the column space of A is going to be some subspace of R3, right? Notice how each column has 3 components. And it's just the set of all the linear combinations of the columns, right? So the span of the column vectors 1, 2, 0, -2, 1, 1, 0, 5, 3, and 1, negative 3, 5. All right, but this is all well and good. This is the column space. It's just there are 4 vectors here, but only 3 components in each vector. So this is going to be a linearly dependent set, meaning I don't need all of these to span the space. So that's why I would prefer, before I write the column space of A, to write an echelon form of A, right? Let's reduce this to I'll put it in reduced row echelon form, like I prefer, RREF. Right? Now you can perform row operations here, and perform Gauss-Jordan elimination by hand to do this. I'm going to save a little time here. Do it on the calculator. Now I have the 84 plus here on the screen ready. All right. So you go second to the matrix menu, over to edit. I'm going to make matrix A here. This is a 3 by 4 matrix. You enter the size first, and the first row, 1, negative 2, 0, 1, 2, 1, 5, negative 3, then 0, 1, 3, 5. Alright, now I've got the entries entered. Get out of there, quit, go back to the matrix menu, over to math, and then scroll until you see, as I've written here, RREF, right? Not REF, which is right above it, right? REF is plain echelon form. It's row echelon form. RREF is what I prefer. Again, they're both fine for when you're trying to find bases for a column space, row space, but I don't know. I just prefer reduced echelon form myself. All right. So put in reduced row echelon form, back to the matrix, matrix A under names. All right. So here it is. I'll write it. Now you can call this A prime or something, or A sub R for reduced echelon form or something. So here I've got A prime. Again, not A. This isn't matrix A. It's A prime. One, or call it matrix B if you want. All right, just something else. 0, 1, 0, 0, 0, 1, and negative 7, negative 4, 3. All right. So what we're doing here, when we're talking column space, what's a basis for the column space? What's a minimal spanning set? Look at your pivots, right? Those are those leading non-zero ones, the leading ones that you see in each row. So here are the pivots. All right, so there's a pivot in just the first 3 columns. Now don't use these 3. Now these 3 are independent, right? And they would span all of R3, right? This is actually the standard basis, 1 0 0 0 1 0 0 0 1. That's the standard basis for R3. Alright, so you could use these, but in general, when you perform row operations, the columns you get won't necessarily be in the column space of the matrix, because when you perform row operations, you're changing the columns in some weird ways sometimes. So don't use these automatically. Again, I could here because these 3 are the standard basis for R3. All of R3 is spanned by these. But what we're going to do in general, right, for all my problems here is the first, second, and third pivot columns in reduced echelon form will correspond to the set of vectors from the original matrix. All right, so this vector here, this vector here, and this vector here, these will form a basis for the column space. Alright, so instead of the column space being the span of these 4 vectors, I'm going to say instead the column space is the span of just those first 3 columns. Right, and the first 3 columns form a basis. So 1 2 0, negative 2 1 1, and 0 5 3. there's a set of linearly independent vectors that spans the column space. Alright, so there's part one. Alright, find the column space, and I'll do all this with the row space after too. Part two is what's a basis for the column space, right? Which is again just this set of these three vectors, these three column vectors that correspond to the three pivot columns in echelon form or reduced echelon form there. So, this set with 1, 2, 0, -2, 1, 1, and 0, 5, 3, right? This is a set of linearly independent vectors that spans the column space. This is a basis for the column space. All right. And I guess additionally for the column space, because this is we're in R3 here, remember any basis for R3 is going to have three vectors in it, right? The dimension of R3 is 3, and we have a basis of this space with 3 vectors. So the column space is the span of these 3 vectors, but that's also just R3. So you could also have said that the column space of A is all of R3. And we could have also said that. And what's the dimension of the column space? It's 3, right? And that's the rank, right? And the dimension of the column space of A, right? That's this rank. That's the rank of A, right? That's 3. All right, we're going to see the same number come up, all right, in a second here when we talk about the row space. All right, so on the next page, same matrix, okay. So I'm keeping that matrix up here, but now let's talk about the row space. Right. So column space, basis for the column space, rank. All right, so same matrix, again, just ignore the wiggly lines around the columns. All right, now I'm looking at what's the row space of A. All right, so the row space of A is, remember, it's the set of all linear combinations of the row vectors. So it's the span of these 3 vectors. Now I'm going to write them as rows here. Row vectors, 1, -2, 0, 1. Right, that first row vector. And then 2, 1, 5, -3. And you could put commas, I guess, between these just to make sure that you know that this isn't -20 or something, and this isn't 21, just to make sure you know that these are separate entries. 2, 1, 5, -3. But I'm going to try to space them out. And the vector, 0, 1, 3, 5. All right. So the row space of A is the span of all these 3 vectors, the 3 row vectors. Right. Any linear combination of these. Now, if you'd like, just to save on some space here, right? Because you notice when I write row vectors, it takes up a lot of space horizontally. You can write row vectors as column vectors, as long as they have the same components written in the same order. They represent the same vectors. So I could also say the row space of A is the span of these 3, these 3 vectors, one with components 1, -2, 0, 1, and then the next one with, again, the same components in the same order going down here, 2, 1, 5, -3, and third one with the same components in the same order going down, 0, 1, 3, 5. And this may look familiar to you, where these would just be the columns of A transpose. Right, if I were to write A transpose, which I'll do down here. Right, so here's matrix A at the top, and if I were to write A transpose, that's just where the rows become columns and columns become rows. So there's a 3x4 matrix. A transpose would be a 4x3, with the first row being the first column, the second row being the second column, third row being the third column. So maybe you can see now too that, and I brought this up in my last video about rank. The row space of A, right, because again these represent the same vectors whether I write them as columns or not, right? The way I wrote them here, they represent the same vectors with the same components. It's just one's written as rows, one's written as columns. But if you look at it this way, the span of these column vectors, you see how these are just the columns of A transpose? So we could say that the row space of A is exactly the same as the column space of A transpose. All right, so again, I know I've brought this up in my last video on rank. All right, the row space of A, or on the row space anyway. I had a video up about row space of a matrix as well. The row space of a matrix is equal to the column space of the transpose. All right. Okay. Now let's see if this is a minimal spanning set. Is this set of these three vectors independent? Well, and going back, you could leave it as A, like I did here. You put it in reduced echelon form, like I have here, and then when you perform row operations, right? When you perform elementary row operations, all of these rows down here are just linear combinations of the rows you started with, right? When you perform elementary row operations, the new rows that you create are just linear combinations of the rows that you started with. So all of these rows are in the row space. So remember earlier I said don't take these columns, the pivot columns, as your basis, but you can take the pivot rows for the basis of the row space. Right. And again, if you aren't familiar with this, please, I pointed this out as well. So each of the in a previous video, right, the pivot rows, okay, these do form a basis for the row space. All right, so here's the row space. It's the linear combination of all these row vectors, or these vectors here as columns, right? They have the same vectors in them, just written different ways. And then here's a basis, right? A basis for the row space of A is the set with these, again, if you keep A the way it is, put it in reduced row echelon form, you can use the pivot rows as a basis for the row space. All right, so the pivot rows are, and I'll write them as rows, okay, are 1, 0, 0, -7, and then the next pivot row in echelon form here, reduced echelon form, 0, 1, 0, -4, and the last pivot row in reduced echelon form, 0, 0, 1, 3. All right, perfectly valid basis for the row space. So not only could you say the row space is the span of this set of vectors, but you could say the row space is also the span of these three vectors. All right, they're linearly independent vectors that span the space. Every linear combination of these three should be able to be written as a linear combination of these three. Right. But also, right, again, I've mentioned, right, so here, here's the row space. You can write the row space this way. Here is a basis for the row space, right, with all my row vectors. And then, the dimension of the row space is that, that rank, right? And we see it's the same value as the dimension of the column space, right? See how there's three vectors in this basis? Same thing, right? And it should be, right? When you find the dimension of the row space and the dimension of the column space, they should have the same number of vectors in them, right? Because they correspond to these pivots, and they have the same number of pivot columns as you have pivot rows. Now, that was one way to go about the row space, right? I could have also, remember the row space is the column space of A transpose. All right, so if I wanted to find a basis for the column space, this set with 3 vectors would also be a basis. Let me I go to A transpose. All right, let's look for just like I found the column space of A, let's find the column space of A transpose. All right, well, the column space of A transpose is this thing, right? The span of these 3 column vectors, and this is a subset of R4, right? And then I put A transpose into reduced row echelon form. All right, and see what we get. Now I have matrix A already entered in my calculator. All right, I have matrix A already entered. So when I go back, I'm just going to put in reduced row echelon form matrix A, but not matrix A. I want to put matrix A transpose. So I just move the cursor back here, and then second matrix, and then over to math, and then number 2 down there is transpose, and then close it. And this is taking A transpose and putting it into reduced row echelon form. Oh, right, I forgot. If you have more rows than columns, it won't do it. So I'm going to go back, edit the matrix here, and I'm going to add another row of all zeros. All right, so this row of all zeros will become the 4th row that's all zeros. When I look at the transpose, will become a 4th column that's all zeros, and I can just ignore that when it gets put in a reduced row echelon form. Okay, so now let's do that again. Re-enter the reduced row echelon form of A transpose, and again ignore the 4th column of all zeros there, and we get this. So again, this is, let's say this is A transpose prime, right? With the reduced row echelon form. So 1 0 0 0 0 1 0 0 0 0 1 0, and that's it, right? Ignore that 4th column. And look at the pivots. Pivot, pivot, pivot. Every column, and remember, don't use these, right? Don't use these columns as a basis, because look at the 4th components. The 4th components of all these columns is 0. So how could I make, this vector here, 0, 1, 3, 5, the 4th component is 5. How could I take these 3 vectors and make another vector with a 4th component of 5 when all of these have 4th components of 0? So don't use the columns as a basis for the column space. Right? You use the vectors in the original matrix that correspond to those pivot columns as a basis, right? So another basis for the row space which is again the same thing as the column space of the transpose, is the set with these 3 columns, right, that correspond to the pivot columns of A transpose in reduced echelon form. So those that 1 negative 2 0 1, that 2 1 5 negative 3, and the 0 1 3 5. Right? So yeah, this is definitely, it spans the space clearly, right? Every vector in the column space is a linear combination of these 3, and we have seen that they're independent by looking at the reduced row echelon form here for A transpose. And yet again, we're seeing that the dimension is 3, right? So the rank of this matrix is 3. All right. Great, so roundabout way of doing that, but still works the same way. Now, don't do a mistake I see made very often. You know how the last one, when I was looking at the column space, every vector in the column space had 3 components, and there were three vectors in the basis. So the span of all those 3 vectors, right, the column space of A was all of R3. Don't make that mistake here. Don't say, hey, there's 3 vectors in a basis. Right? There's 3 vectors in a basis, so the row space is R3. No, it's not. All these vectors have 4 components. So this is a subspace of R4, right, which is not necessarily R3. Okay, do not just say, oh, it's R3, because there's 3 basis vectors. Right? Look at how many components are in the vectors. Right? These are not even from R3 anyway. All right, so be careful with that. Now, if I had a basis with 4 vectors and each one had 4 components, then it would be R4, right? The span of those 4 independent vectors. Right. Okay, now one other thing to point out here when it comes to a matrix and its transpose. If you notice from the last problem, right, the dimension of the row space, right, the dimension of the row space, right, is the same thing as saying what's the dimension of the column space of the transpose, right? Because the row space of a matrix is the column space of a transpose. Well, remember, the dimension of the column space of a matrix, that's called the rank. Right? That's the rank of a matrix. So this is the same thing as the rank of A transpose. But we also stated earlier that the dimension of the row space, that's also going to be the rank of A. Right? The dimension of the row space of A is the rank of A. The dimension of the column space of A transpose is the rank of A transpose. So what we're seeing here is that the rank of a matrix will be equal to the rank of its transpose as well. All right. So let's keep that in mind. You can use that result at some time in the future as well. All right, so I'm going to do one more example of this. All right. Where this time I'm not going to write the transpose, because there's a lot of entries here. So this time I have a 4-row, 5-column matrix, right? 4 by 5 matrix, and I'm doing the same stuff, right? So first I want to find the column space of A. Well, before I do any of this time, instead of writing the column space as the span of these 5 columns, well, there's 5 vectors from R4, so it's definitely not going to be independent. It's going to be a dependent set. So I'm not going to write out the column space of A as the span of these 5 vectors. What I'm going to do is put this into reduced echelon form. Alright, so again, we'll call this like A prime or something, or matrix B, whatever you want, right, just something else. And we'll talk about the column space and row space from there. Alright. So back to the matrix, I'm going to go over to edit again and just edit matrix A again here, and this is a 4 by 5 this time, right? And first row 1, 0, -2, 1, 0, then 0, -1, -3, 1, 3. Next row, -2, -1, 1, -1, and 3. And last row, 0, 3, 9, 0, -12. Okay. So get out of here, put into reduced echelon form. Now, I'm not putting the last one I had up because that was for the transpose. And reduce echelon form of, you could use matrix A transpose and that would still tell us a lot of information, but I'll just go to A here. Alright. So in reduced echelon form we have 1, 0, 0, 0 for the first column, 0, 1, 0, 0 for the second column, -2, 3, 0, 0 for the third column, 0, 0, 1, 0 for the fourth column, and 1, -4, -1, 0 for the fifth column. Okay, so look at the pivots. These leading ones in the rows. There's one there, and one there, and that's it. There's no leading one in that fourth row. It's all zeros. Alright, so the first, second, and fourth column vector of A form a basis for the column space. So the column space of A is the span of those three vectors. So 1, 0, negative 2, 0. The second one, 0, negative 1, negative 1, 3. And the fourth one, right, 1, 1, negative 1, 0. Right, which is a subspace, right? This is a subspace of R4. It is not R4, right? And this set forms a basis, right? The set with these three vectors. Just drawing them again. All right, this again is a basis for the column space of A. And so the rank is again 3. Now just because these only examples I have here have a rank of 3 doesn't mean that every matrix has a rank of 3. Please know this. All right. Come across all sorts of different examples. All right. So the rank of the matrix is 3. I wrote the column space out where it's all linear combinations of these 3, which are linearly independent. Great. So that means, right, any linear combination of these 5 can be written as a linear combination of these 3. Also, too, remember I said for the column space, for a basis of the column space, do not use the pivot columns in reduced echelon form. Right, because if I used 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, look at the fourth components of all these. They're all zeros. So how could I make this vector with a linear combination of these 3? Because this vector has a fourth component of 3. All of these 3 have fourth components of 0. How could I make a fourth component of 3 out of that? All right, so please, again, do not use the pivot columns of reduced echelon form. Use the columns that they correspond to, right, the first, second, and fourth, from the original matrix as your basis for the column space. Okay, wonderful. All right, and then off to the side here, we can do the row space. All right. The row space of A, again, very simply, it's the span of these 4 vectors. There's 4 vectors from R5, right? Every row vector has 5 components. Now I'm going to write them as columns just to save on space. So the row space of A is all linear combinations of these 4 vectors, but we're seeing from reduced echelon form that I don't need the 4th one. All right. And again, when I put A in reduced echelon form, I will use the pivot rows as my basis for the row space. Right, because every time you perform row operations, you're just creating new linear combinations of the rows from the original matrix. So these 3 pivot rows are in the row space, and they do form a basis for the row space. So the row space of A is the span, and again, I'm going to write them as columns just to save on space, of this row vector, again, written as a column here. So 1, 0, negative 2, 0, 1 from R5, and then this row vector, the pivot row, right, 0, 1, 3, 0, negative 4, and this row vector, right, 0, 0, 0, 1, negative 1. All right, so every linear combination of these four rows can be written as a linear combination of these 3 rows, right, these 3 pivot rows. And again, it's fine to keep these. Okay, and then that set, of course, forms a basis. I'm just going to abbreviate this. Let's call this vector 1, vector 2, and vector 3. All right, so the set with vector 1, vector 2, and vector 3, as written up there, is a basis for the row space, or the column space of A transpose, right? The row space of A, or the column space of A transpose, same deal. And then finally, because there's 3 in there, right, the rank of A is 3. All right, so you're seeing again how the rank of a matrix is the dimension of the column space, the dimension of the row space, which therefore would also be the dimension of the column space of A transpose, and also the row space of A transpose if you looked at A transpose and put that into reduced row echelon form. Look for pivots there. Alright, so pretty simple stuff, I feel. Take a matrix, put it into reduced echelon form, or just echelon form would be fine too. You're still just looking for pivot rows and pivot columns. The column space will be the span of not the pivot columns, but the columns the pivot columns correspond to in the original matrix. And the row space will be the span of the pivot rows of reduced echelon form or echelon form. Right, you can use those are fine. And then the rank, again, the rank is just simply the number of vectors that are in a basis for the column space, or a basis for the row space, or just the number of pivots that you found, right? There are 3 pivots here. Rank is 3. Great. All right, so I hope you enjoy practicing problems of this nature, and thank you very much for watching.